Okay, so our next speaker is Dr. Tommaso Chiarotti from EPFL that is going to introduce dynamical extensions of DFT+U. Tommaso, please.
Okay, so thank you very much for the kind introduction. So yes, I'm Tommaso Chiarotti, and I work in EPFL. My collaborations for this project is Hubbard and Nicola Mazzari. So this is a long-standing project that we have for the love of God. Yes, it's the clicking problem. Yes. Okay. So anyway, so I don't want to, let me just start the timing. Yes, so that I don't go wrong. Okay, so the point is that, so I don't want to, let's say, I don't need to remind you, let's say, the fact that density functional theory is a very successful theory. So this school is all about this, let's say. Now, since this picture wasn't shown before, I thought actually to add this slide just because to actually see the successes of DFT. Now, one can ask, why is density functional theory so successful? And the simple answer, the very small answer is crystal structure predictions. Okay, computational crystal structure prediction. Okay, sorry, my bad. But there is a fundamental limit of density functional theory, and this fundamental limit has to do with the spectrum. So we are talking about on a sham DFT. So I will not enter into the very, let's say, hard details of all this stuff. But let's say that this is the Cone-Sham spectrum in blue for the simplest material possible, silicon, which is actually an homogeneous electron gas near the Fermi level, almost a free homogeneous electron gas, as Nicola showed us. So this is the simplest material possible. And you see the astonishing failure of density functional theory. In green, we have a corrective thing to density functional theory that will be presented tomorrow. But the point is that you can believe that the green line is the correct result, if you want, for the quasi-particle description of this semiconductor. Instead, the Cone-Sham spectrum, as you can see, is way off. Okay, but then, let's say, spectral materials are not Cone-Sham spectra, are not quasi-particle spectra, sorry, are spectral functions. So again, I will not enter into the details of this, in this talk, let's say, but just to give, let's say, a very brief perspective. So this is the quasi, sorry, my hand is shakes a bit all the time, but let's say that the point is that the yellow line there is the quasi-particle band, which is represented into the Cone-Sham spectrum, as this black line. And what you have actually in reality, so when you do angle resolved photoemission spectroscopy, you have these things, which are called satellites. So you have a transfer of weight of the probability to extract an electron from the quasi-particle band to satellites. And this cannot be predicted by a static, and we will see what I mean by static theory. We need a dynamical theory. And so why, so a correct answer, a correct question to ask is, why is this thing to predict so hard? And the simplest answer is that we are not trying to predict a system. We are trying to predict an open system. So we are dealing with open quantum mechanics. And what is the open thing? The fact that in angle resolved photoemission spectroscopy, you shine a photon in and you get an electron out. So you see the electron must go somewhere. And this is indeed a system which interacts with a bath. All right. And this is actually the really hard thing to get. And as you can see, so it's closed, it's open quantum systems. There is no Schrödinger equation. The energy is not conserved. It's not Hamiltonian, the system. Okay, so very hard stuff. Anyway, so there is a nice theory to deal with spectrum, if you want to predict the spectrum, a very nice formalism. And of course, it has to do with embedding. And so this is where Green's functions come in. All right. So, so why do we need indeed the Green's function? Well, because this is a bit formal, let's say, but if you think to write the n particle Schrödinger equation for your system, which has all the information that you want, let's say, you can do an embedding, you can have an embedding idea, which is, let's say, divide the degrees of freedom, and you can, let's say, write only one equation of this n particle Schrödinger equation by simply using, this is a linear system, sorry. You simply use the second equation into the first one, and you get something like this. And this is the one particle Green's function of the system. Now, what happens when you do something like this? It happens that you have only one equation to solve instead of n coupled equations, the n particle Schrödinger equation. So you have done this, so you must have lost something, right? You cannot do this without losing anything. And what you discover actually, and this is one of the purposes of talk, of the papers and stuff, is that you lose a linearity. So you are entering into a world which is non-linear. You need to solve non-linear equations to actually get the result. And so indeed, you need to solve this secular equation, which is, let's say, the counterpart of the Konesh-Hammer equation, which is a linear equation. This instead is a non-linear equation. It's called the Dyson equation. And indeed, this non-linearity is actually brought by this potential here, which is called the self-energy, which is a dynamical potential, and that gives you the flexibility to actually predict the spectra. Okay. And this is, so Green's function theory in a nutshell, let's say. So this is a school, so I thought to actually put this slide. So what are Green's function? Well, those are expectation values of this kind of propagation operator. Anyway, so the point is that with Green's function, you predict, you can, if you know the exact Green's function of the system, you can actually do expectation values of one-body operators. Then you can do, so ground state properties, to be clear. Then you can do, you can compute the spectral function, which is actually related to the Harper's experiment. All right. Then what is really cool, let's say, of Green's functions is it is a perfect analogous to density functional theory, which means that there exists an energy function of the Green's function. Those are many names: Klein functional, Lustiger-Walsh functional. It is an energy function of the Green's function. It is a more complex object than the density functional, the density function of the energy. Sorry, the density function of the energetic function of the rho, anyway, so sorry. But the point is that it exists. And of course, the nice thing is that if you derive the function, so the first derivative actually gives you the Dyson equation exactly as if you derive the energy function with respect to the density, the density function with respect to the density, you get the Konesh-Hammer equations. Now, as I said, let's say this is the features that you're never going to get in density functional theory, which is actually the result of the Harper's experiment. So those are very, very important, as I said, so quasi-particles, satellites. And with this, you brought in the language of final lifetimes of particles. Okay, now, so this is, let's say, some state-of-the-art results. Of course, I cannot cite everything, but these are computed with dynamical mean-field theory. This is lanthanum nickel oxide. This is constant vanillate. This is indeed an Harper's prediction. Here you have the experiment. Here you have the result of the calculation, the dynamical mean-field theory calculation. You see there is a very good agreement, let's say. Konesh-Hammer DFT is terribly wrong. It has to be wrong for the fundamental reason. It is also wrong because it doesn't predict let's say, the different weights of the spectrum as you go along the band. But as I said, cool thing is with Green's function theory, you have an energy function. You can predict energies, And so you can do also thermodynamic properties, which are ground state properties, for example, phonons, exactly as you do with DFT. Okay. Now, and so this is in some sense where we stand, if you want. So, so there are some people that try to, there are extensions of density functional theory, time-dependent density functional theory. This has to do with neutral excitation. This is a simpler problem, if you want, because the sequence is thick laws. Okay. Then there are spectral theories, which instead have to deal with non-linear quantities, dynamical quantities, and this is instead to predict charge excitation, exactly the result of artifact experiments. And then you have a wave function method that instead you need to go, you want to do it if the material is really, let's say, complex to solve with approximations. And so indeed, so the take-home message from all of this, let's say, is the fact that beyond the DFT in the spectral, so in the spectral arrow, is useful for spectral properties, but also on the side, maybe you deal with functional quantities approximation that are also better to predict ground state quantities. Okay. And so indeed, so I try to summarize what you can do now. Let's say, so indeed, this is a very brief, very crude slide, but let's say, very engravingly, let's say, if you want to go, let's say, with along this arrow, so what you want to do is actually to predict spectral and thermodynamic, which are ground state properties of a material. Well, you can use many body perturbation theory, but when you try to use it, you actually discover that you can really not get both of the things together due to the complexity of the theory itself. Then dynamical mean-field theory is a very successful theory. It does have the flexibility to allow you to predict exactly as in Kohn-Sham DFT, both the properties, but better for the spectrum for sure. But still, it is tricky. It is dynamical mean-field theory. It is a very complex, let's say, clever construction. And it is also, but it is very expensive also. And tomorrow you will see that actually there is a theory which is a quasi-particle approximation to dynamical theory, which is called the Koopmans compliant functionals, in which in some sense you are here and you can get at least the quasi-particle that I showed at the beginning of the talk for silicon, so for simple materials. Okay. But this is our grand plan, let's say, instead. So the grand plan is to go beyond Kohn-Sham DFT, is to actually deal with dynamical quantities. As I said, the goal of the whole project of the life is to predict thermodynamics and spectral quantities together, and we will do this in this manner. So first, you need to define a formalism, a computational suitable formalism to deal with dynamical quantities. Okay, then you discover when you try to do stuff that something really nice happens, which is related. It is in some sense it has some connection with the Kohn-Sham system, let's say. So you see, then you use it in practice. Let's say you design a new functional. This had to happen, let's say, at some point, because functional that exist are very complex and very expensive to compute. So to actually compute material properties, we need to define a new function. And you actually discover that this new function is the natural extension of DFT+U with the dynamical screening. And then you compute actually these properties for a real material. Okay. Now, so this is what we thought is suitable to implement these dynamical quantities. So as I said, so here you need to deal with time moderate propagators, which are operators, let's say, expanded in frequency. So let's say that you have a new axis with respect to density functional theory, so the frequency axis. And so this brings, a complexity more, because you need to deal with a dimension more. This dimension is also non-linear in some sense. I will explain why. But still, you need to deal with this thing. And so in the end, what actually happens in practice is that you need to do a lot of convolutions. And so what is a good way to integrals, let's say, over frequency? A good way to do integrals in a computer is to write something on a basis, like the plane wave basis, and you compute the integral because you know how to do Fourier transform. Here instead, what you do is that you write dynamical propagators, for example, the Green's function, in this representation. And of course, if both of these propagators are expanded in this form, let's say, the integrals are all analytical, just the application of the Cauchy-Residue theorem. Now, this is not new at all. Actually, Ben-Farid have already, let's say, taught something really similar and actually showed that this is actually suitable for time order propagator, let's say. Then, as I said, analytic convolutions, they happen, and also analytic thermodynamic, it happens, let's say. And so the other thing that we discovered is the fact that this form allows you to solve the nonlinear equation that is the Dyson equation, and I will tell you why, let's say, how. So yes, so we pass to this part. So to do this, so to understand, let's say, what is the nonlinearity brought by dynamical potential, we need to, let's say, cast this problem into a mathematical problem, if you want. So now, for non-interacting system, if you want to find the Green's function of an Hamiltonian, let's say, you need to solve this equation. Now, this is it an equation to solve? It's just an inversion of an operator, yes, but how do you solve this equation? Well, you write the eigenvalue problem, right, of this operator. So you have eigenvectors and eigenvalues, and then the inversion of this operator comes out naturally as the sum of the eigenvectors above, eigenvalues on the bottom. So this is actually an equation. It's not only an inversion if you think it in a matrix sense. Fine. Then can we do exactly the same for the Dyson equation? And the answer is yes. I mean, you can. Fine. But you see immediately that there is something very strange that happens. The fact that the operator depends on the eigenvalue itself. And this is what is the nonlinear nature of this equation. And actually, mathematicians, they do study this very recently, let's say, so 2000. So we are talking about the mathematics it's happening right now, let's say, but this is a nonlinear eigenvalue problem that you can solve. And the nice thing is that if you're able to solve it, the solution formally is exactly the same. So you have nonlinear eigenvectors above, nonlinear eigenvalues on the bottom, but formally, let's say, conceptually, the thing is exactly the same. So the problem was to ask how to solve this equation first in a computer. What happens, so what do people do right now, let's say? So this is so because in some sense, many bad perturbation theory, you need to solve this equation. So how people manage this thing before us, let's say? Well, they manage just discarding of diagonal elements of this operator, and now this equation is not an inversion of an operator anymore. It's just an inversion of a scalar. And what happens if you do this? So this is Friedrich, 2013, and in the black line you see this is a topological material. So of course, when you neglect of diagonal elements, when there are band crossing, it's going to be a disaster. And this is exactly what happens, and this is particularly interesting because it's a topological material. So if you mess up the band crossing, the material is not topological anymore. So instead, if you solve the exact equation, they didn't solve it in a way. They solve it via simply inverting the operator at the frequencies. They do not find the solution of you just find the solution on a grid. But anyway, you can do that, and you actually, let's say, demonstrate that actually it is useful and very important when they are band crossing to solve the full equation. Okay, now, but this is actually our strategy instead, is not to find the solution on a grid, is to find the solution of the equation. And so we need to indeed to solve the Dyson equation, the nonlinear eigenvalue problem. But the nice thing is that the fact that if you write the self-energy on this basis, let's say, what happens is that you can build an equivalent system, a non-interacting system, which has the same Green's function as the system that you wanted, as the interactive system that you wanted to study. So you see, it's exactly as on a sham. You build a non-interactive system, which has the same ground state density with respect to Constant. Here you build a non-interactive system which has the same Green's function. Now, this is actually a paradox. It cannot be done. And indeed, there is a trick. The fact that this system is larger. It is larger by the degrees of freedom of the self-energy. So in some sense, what you have done is that you invented ghost particles that are not non-interacting, and you write an effective Hamiltonian for this system, and then you actually have the Green's function for this system. You project into the space without the ghost particles, so into the subspace, and you get the exact Green's function. And I will explain you why. Let's say, in some sense, to do a sketch of the proof in this slide. All right. So it's not complex. It has to do only with embedding theory, if you want. So why did I explain this? How to get the Dyson equation before? Is exactly because it is helpful to understand what happens in the algorithmic inversion method, which is our method to solve the Dyson equation. Well, so as I said, embedded degrees of freedom, you have the n particle scaling equation, you divide the system of equation in two, you use only the first equation, like taking the second and writing into the first one. Okay, now you need to solve, instead you are here now, okay, and you have the sum of the poles here with one pole representation of your self-energy. Fine. You just rewrite the self-energy in this way, you see? Okay. Now this looks pretty similar to this. It's actually formally the same. And you know to solve this nonlinear equation. You need to build up this Hamiltonian if you want, right? Exactly. So the point is that if you solve this Hamiltonian, you diagonalize it, you project back to the H0 inverse space, you get exactly the sum of the poles of the solution of the Dyson equation. So you get Dyson orbitals, non-orthogonal, non-linear independent Dyson orbitals, and eigenvalues. Okay, so this is exactly how you solve, let's say, a nonlinear problem. If you want, mathematicians have already done this construction, which is similar, let's say, but I have another slide. So the point of actually here is the fact that, okay, but one can ask, sure, but maybe you are just, rewriting the n-particle Schrödinger equation in the end, right? Well, no. First, the particles are not interacting in this system. Second, the degrees of freedom that you have, so the number of poles of the self-energy in a real material are, you can count them, how many poles. I think it's 7, 5. So an infinite number of particles, which is a crystal, it is remarked to 5 poles. So you see 5 ghost particles to solve exactly the Dyson equation. This is a very good, let's say, way of rewriting degrees of freedom. Okay. And as I said, so in some sense, this is nothing new in some sense. So because indeed, if you look at the mathematics, let's say, this is very much related to companion diagonalization, companion solution of nonlinear eigenvalue problems, of rational polynomial eigenvalue problems, actually. And it is actually also related to some techniques that have been used in electronic structure already, for example, to solve in a different context, but to solve the polarizability Dyson equation and all of this. Now it is very formal, let's say, very understood with all of this. Okay. Now, okay, and we have used, let's say, all this machinery. Let me look at the timing. Okay, 23 minutes. So we have used all this machinery to actually, we took the homogeneous electron gas, which is a very simple example. We applied the GW approximation, and we computed at several densities, let's say, the spectral function, which is indeed so in every quadrant, let's say, so in every, yes, here there are the spectral functions. The point of this is that the physics of the electron gas is very plasmonic at these densities. So GW is okay in some sense, and we wanted to to test our formalism, the sum of pose, the algorithmic inversion, on all of this, and let's say it works. But the point of all of this is that you don't only get the spectral functions, you get also correlation energy. So you get thermodynamic quantities if you want. We will see them phonos at the end of the presentation for real material. Okay, but then we wanted to go to real materials, right? So we wanted to apply our formalism to real materials. And so we sat down and we said, okay, fine, but what exactly do we want to do? Do we want to implement many-body perturbation theory? Do we want to implement an approximation of this, which is called GW? What do we want to do? What materials do we want to analyze? Okay, and we sat down and we said, well, we want to tackle, interesting materials, for example, nickel oxide, tungsten vanadate, iron oxide, all of this, right? So these are very interesting materials. These are materials in which we are sure that, we can guess that approximate semi-local functionals, like GGA and stuff, they will perform not perfectly, let's say. So we want to tackle exactly this problem. And so GW yes, it's not really very suitable for these materials because in some sense it tends to delocalize anyway. Then dynamical MIFI theory, it is very suitable, but it is very tricky and very expensive. There are a lot of approximation, a lot of assumptions that you need to make. For example, that your material is a lambda model to make the DFT works. And then we understood instead that localized GW, which I will explain a bit, it yields promising results for this, for example, for this tungsten vanadate, and namely here you can see the quasi-particle. No, it's 25 minutes, Andrea. So it's I understand, but I think that so it's a disaster. I mean, what the hell? So I can finish at I don't know 32. Anyway, so I will be brief. So anyway, so the point, but the cool stuff is still to happen. So anyway, the point is that it is not written here, but actually this bandwidth, these are the T2G bands in tungsten vanadate. This is the Fermi level, if you want. So the bandwidth here is really comparable to experiments, whereas instead the GW is not, and LDA here, but PB, we see the results. It's not working. So localized GW looks promising to actually compute these materials. But the problem of localized GW is the fact it's a spectral theory, right? So it's just a self-energy, if you will, just a potential. It doesn't tell you anything about the total energy. Okay, so what do you have to do in this case? You need to functionalize the theory. So you need to write an energy functional that has that self-energy as derivative, right? So, and this is what we discover actually be exactly the dynamical extension of the Hubbard function. I will explain why, let's say. Yeah, so this is just a framework that you work with, let's say. So this is exactly the counterpart of energy functionals in DFT with instead the Green's function formalism. This is the Klein function, is the function of the Green's function. Here, rho is just the density is just a contraction of the Green's function. So this is a functional of the Green's functions, right? And exactly as happens with Konesham DFT, let's say, there is a term that you don't know, and this term is exactly the exchange correlation term that you need to approximate. All right. So what do you do when you don't know? You just sit down and write an exchange correlation term and hope, let's say, and physically analyze if this makes sense or not. Okay, so this is the term that we wrote. All right. So this is the phi functional of we discovered to be localized GW. And the point is that, so let's try to break this down. So U here is just, I didn't tell you what it is. It's just a parameter here. It will be the screening anyway. So the point is that, so what happens if U is frequency independent? So if U is static, this goes out of the integral. And you do first the omega prime integral, and this becomes N, right? Then you do the omega integral, this becomes 1. And you do the omega integral again, this becomes n. I didn't say that actually G is not the Green's function, it's the projection of the Green's function onto a number manifold that you choose. And so you see that actually you are exactly building, let's say, a generalization of the DFT plus of the simplest, let's say, rotational invariant DFT+U functional, but with a screening which is dynamic. All right. So again, if the screening is static, this goes back exactly to the DFT+U functional that Matteo explained, Yuri explained. And so this function, you know, it has the promise to work good for total energy because it's just an extension, it's just a generalization. But would it be good for spectra? Well, yes, we have designed it. If you take the derivative of this function with respect to the self-energy, you end up with this thing. And you see that this is actually exactly localized GW. It is G, a local G, times W, a local W, U, the screening parameter. And so indeed, if you look at the last author of this is, I don't remember anymore, but anyway, if you look at this paper, it's not written in this way, but can be recasted, the self-energy of localized GW in this way. And there is just a double counting term, exactly as for DFT+U. You need to have a double counting term because you are correcting DFT in the end. What you want to do is to correct DFT. Okay, and so just okay, let me look. Okay, so just a brief, let's say, understanding of what is U. As I said, it has to be a local average of the screening W. And what screening? Since we are doing localized GW, it is clear, RPA screening. So you have to calculate the RPA screening, average it over the manifold, over the Hubbard manifold, and you get this U. And then what you do actually with my code is that actually you compute the sum of the poles for U, the form that I to actually use all the machinery of solving the Dyson equation and calculates the thermodynamic properties. But anyway, this is how the screening looked like in Strontium vanadate. So a very real case example, exactly. So a brief reminder, let's say. So this is different than, so if you take the static limit of this U, you don't get the density functional perturbation theory U that actually Yuri calculates, but this is not a problem because this is actually driven by the fact that we are doing localized GW. So it has to be an RPA screening and not a CRPA screening. Okay. Then what happens when you do the actual calculations? Okay, so these are the steps that I will spare you, let's say, just to say that actually when you compute the spectrum, it's not the spectrum anymore. It's exactly as DFT. You compute the total energy for this material finally with with a dynamical theory. What I want to stress here is the fact that the strontium vanadate, it was highly debated because it was the prototypical example of dynamical mean field theory. Why? Because density functional theory, as you can see, so this bandwidth, these are the T2G bands. Sorry, this slide, it looks better on the computer, but so the point is that the yellow are the results of my code, let's say, so are the results of localized GW. This bandwidth is correct. We have already seen it in the Miyake paper. Okay. Now, the point is the fact that so the bandwidth is correct. Okay, fine. But why does the bandwidth shrink with respect to Cone-Sham DFT or DFT+U? You see, the bandwidth shrinks. It was taught by the dynamical mean field theory community because of these two bands. So here you cannot see anything, but in the computer you can. So if you look at the article, it's very clear. There are two Hubbard bands here, actually. All right, it was taught that these two Hubbard bands were to give the shrinking, all right? So this is actually the Mott physics, if you want, happening. Instead, it is absolutely not true. It was discovered before. It is not from us, actually. The fact that this is not these are not Hubbard bands. These are actually instead plasmonic bands. with GW plus DMFT, you can do this analysis, but actually here with this theory, this analysis is as simple as you can, as you want. Since these two satellites are actually brought by exactly this peaking U from the convolution, if you switch off this peaking U, these two satellites, they disappear. So you understand that the fact that the band is shrinked is the frequency of the U, and the fact that these two plasmonic bands appears is the fact that you have a plasmonic excitation between the T2G to G bands, I guess. Okay, so the physics now of Sylvain is clear. There is no Hubbard physics, it's just plasmonic physics. Very good. So yes, so you can compare it, the bandwidth with experiment, with GW plus DFT. The results are perfect. So nothing to say about this. The only thing is that indeed, so with all of this, you don't only get a normal spectrum, but you also get the phonons. So you get the total energy, you get all the things that you would get with the density functional theory, so the bike models, the phonons, and you can actually compare it with the DMFT results of Christian Aule, and they go in the same direction. They are not the same, but there are issues, let's say, both sides that we are fixing in some sense. Okay, now so the outlook of this, and there I will finish. The outlook of this is the fact that, of course, now that you have all these techniques, you want to compute several, right, materials. Clear? Now, what I showed to you is a one-shot calculation. But since there is a functional, well, you don't want a way to minimize it, right? It's actually, the Klein function is stationarized by the self-consistent solution of the Dyson equation. So you want to implement self-consistency in all of this. This is incredibly important because it will give you the possibility to use Feynman theorem to actually compute the forces and, in some sense, to compute, to do generalization of density functional perturbation theory. All of this was made, let's say, into the, so it's one of the most fundamental ingredients of all of this, formally, computationally, let's say, is the trick that you are actually working in a non-interacting system in the end, because you have mapped it exactly to a non-interacting system by the formalism itself. Okay, and so these are the conclusions. So just wanted to stress the fact that the algorithmic inversion method on some of our poles was made to deal with dynamical potential. Indeed, this provides these functions, Dyson orbitals, thanks to the algorithmic inversion method, excitation energies, which are the poles, lifetimes, total energies. Then we wrote this function, the Numerical Hubbard function, which is the generalization of DFT+U. It works good for the total energy, of course, DFT+U does, but it works also really good for the spectrum because localized GW does. And then there is this application, these two papers. And with this, I thank you for your attention.
So, are there questions?
So thanks, Tommaso. So I have a very simple question for you. So I think I understand why this sum over course is important in everything.
Yeah.
What was not clear to me is if this algorithmic inversion has anything to do with the second part of your talk, this dynamical Hubbard function, or they are kind of included.
No, they are. So if you want, the algorithmic inversion is the way to let's say the most suitable way that we found to implement it. But the dynamical Hubbard function, it exists on its own, let's say. So it's just it's a new function of material science, if you want, is to compute the spectrum and energies in this formalism. And just to implement it on a computer, the sum of the poles and stuff are really.
So you use the sum of the poles, but you don't use it.
Of course, I used it. I mean, so sorry, because I need to go fast on that thing. But yes, so indeed, so in some sense, when you solve this equation, you need to solve it.
Okay, when you express it as a sum of the poles, you automatically get
the solution of this. Exactly, you get the fictitious system exactly, so you can solve the equation, and this is fundamentally important if you want to compute, the thermodynamics. So if you want to integrate, you cannot discard of diagonal elements. If there are band crossings, the total energy will be completely wrong.
Maybe
so,
so.
Because the number of particles has to be conserved. So you see, so if you discard something, the number of particles is really something that is so small variation will give you totally bad, let's say, result. So in some sense, either you do this or you find another way to solve this equation to get the thermodynamics properties, or you don't.
And the line with all of that comes from the fact that it's DI, so the Dyson orbitals are not orthogonal, so
exactly.
From there you don't see the line, but actually
yes,
okay.
Indeed. So here these are not orthogonal. Here are complex.
Okay.
So those are complex, so you get the lifetime from the complex thing. Yes.
Well,
thank you. So I'm interested in the connection. So if you do the static limit of your beta, and then you just use it, yeah. So that to go to zero, I guess you don't go to zero. You find that you will.
No. We go. It seems strange, but yes, it goes exactly to zero.
If let's say if you use it, then you will,
Yes.
Sort plus U. What do you get?
Yeah. So no. Of course, no. And the reason is, I tell you the number. So you get something which is around, I think, 1.7 electron volt, which is nothing in comparison to 6. So this is obtained by the U with U, so 6. If you apply 1, you exactly stay on DFT, actually. Okay, I think that.
Do you understand why? What's the connection?
So what the connection between this static limit and the CRPA from and so no one understands the connection, but what you can understand is the physics if you want. So if you do the static limit of CRPA, this becomes a number which is more comparable, 5, 7. The details, let's say, so the error bar is still there, let's say, because you correct the curvature of the functional. Here instead you just guess it by understanding what are the transitions that gives you exactly that screening if you want. But the point is that so the physical connection is this. So the physical connection is that so if you look at the fact that in any case U has to deal with charge transitions, if you want. So the charge that goes into the manifold, outside the manifold, let's say, then it is a good justification to take the CRPA, because you don't want to count the excitation that are inside the manifold itself, right? So you need to probe you need to, let's say, the derivative with respect to n, with respect to lambda is exactly the particles that goes out, right? So this is the justification to take CRPA in a very crude way, and maybe Matteo can say much more, I think, on the fact on how do the two things connect, let's say. So the curvature with respect to CRPA in some sense. But instead here we are completely justified, since we are doing localized GW, to take RPA. And yes, and the really interesting thing is that in metal it was like this. In insulators, in which DFT+U, let's say, works better and tougher, it works exactly as DFT+U. So it opens the gap exactly in the way, so it takes the T2G band and it opens the gap exactly the same way that DFT+U does. So in some sense, there is no contradiction. In some sense, it's just that there you wanted to fix, the curvature. Here instead, you add the screening. And so to physics, same result, because it's a correct one, if you want. Yeah.
Okay, so I don't see any other questions. Let's thank Tommaso.